and then I'll talk more about the classes. These are the three required courses you have to take. There's Calc 3, which means of course Calc 1 and 2 are also required, and then there's linear algebra. Those two classes are taken by all engineers, computer scientists, and physics majors regardless. So look at that, you're already on your way to a math minor if you study one of those other majors. The next required class is your proofs class. As I said before, this class did not sound fun to me years ago because the only times I'd done proofs were in geometry, and honestly side angles, side triangles, and two-table proofs bored me. If that's you, don't worry. This class is much different, and I finally learned I actually do find those proofs interesting. This class is where you learn how to prove that the square root of 2 is irrational, or you'll learn tools for proving whether using only a 32-gallon jug and a 6-gallon jug, you can fill up the 32-gallon one with exactly 10 gallons, assuming you had infinite water, which involves number theory or the study of integers, a foundation for cryptography. And there are plenty of specific proof techniques you'll learn in order to do these problems. This class is required because lots of upper division classes have it as a prereq. Additionally, lots of high-level math courses, especially in pure math, involve rigorous proofs. Now before I move on to the other classes, I want to emphasize something. Throughout most of school, math is like a ladder. You get to pre-algebra, then jump to algebra 1, geometry, algebra 2, pre-calc, and so on. You always need one before the next. Once you get to college though, it becomes more like a tree. For example, after calculus 2, at least at my school, you can take linear algebra, and you can also take a proofs class that most majors don't take. After proofs, you can take graph theory and number theory. After Calc 3, you can take vector analysis, and then after that, differential geometry. Or after Calc 3, you can take numerical analysis. I could go on, but hopefully you get the point. And note, these are specific for my school. Others will be a bit different in terms of their prereqs. But okay, now let's get into all these other classes. As you can see, you're required to take 16 units, which means 4 of these classes. And you can pick whichever ones you want so long as you have the prereqs. I'll go over a few and explain who they might be right for depending on your major and interests. The first one I'll discuss is vector analysis. This class goes into depth on Green's theorem, Stokes' theorem, and the divergence theorem. For those who have not taken Calc 3 yet, if for example you have a complicated vector field, maybe representing a whirlpool of some fluid, and you move an object through it in some weird path, it can be difficult to calculate how much work is done on it or its final velocity. The techniques you use in this class simplify that process. Whether it be a magnetic field, electric field, gravitational field, and so on, when something moves through a field of complex forces, we need vector analysis to analyze what will happen. This class is required for physics majors at my school, and is a good one to take for electrical engineers who are going into wireless communications because electromagnetic waves are represented by vectors and you will do vector analysis. Next one is graph theory. This class is great for computer scientists who want to learn more about the field, because they already do learn some in other classes. Graph theory is not the graphs you're thinking of. It's when you have a bunch of nodes or dots and lines that connect them or edges. This could represent a network of computers that are connected where you want information to take the shortest path from one point to another. Nodes could represent classes, and edges could mean at least one student is in both classes. Like this edge means at least one person is in both this chemistry class and English class. If you want to develop a scheduling algorithm for finals week such that no one has conflicting times, you would need graph theory. Whether it's determining shortest paths, compatibility according to a dating profile, or an algorithm to rank chess players based on who's played who, you need graph theory to help with these. Next up is differential geometry. This uses calculus techniques, among a few other prereqs, to analyze problems in geometry. You'll analyze the actual curvature of certain shapes and surfaces. If a line can be said to have zero curvature since it's straight, how can we quantify the curvature of other shapes and surfaces? Well, it involves calculus. You'll also learn about geodesics, where in the most basic sense you know the shortest path between 2 points is a straight line. But a geodesic generalizes this to curved surfaces. One textbook says, geodesics are the curves in a surface that a bug living in the surface would perceive to be straight. This class is fairly advanced, but it dives into depth on complex curves and surfaces. The concepts are a foundation for understanding Einstein's general theory of relativity and the curvature of space-time. In fact, they say differential geometry is the language of Einstein's general theory of relativity, but it has plenty of other applications as well. Differential geometry is really important for physicists going on to grad school, but in a bachelor's you may or may not see it. Then the class can be interesting for engineers, but is not something you will likely need during your career. Moving on, complex analysis is a class dedicated to complex numbers, or numbers with an imaginary component to them. These actually do have a ton of applications, especially when analyzing waves of some sort. Complex numbers will come up. You learn how to do calculus in the complex plane. And when I took this class, actually on day 1 and 2, we proved a bunch of trig identities you learn in Algebra 2 or pre-calc using complex numbers and Euler's formula. Complex numbers apply to signals, quantum mechanics, relativity, control systems, and several other fields. Physics majors and electrical engineers would benefit from this class the most, and at many schools it is required for one or both of those majors. The class does go into much more depth than most would need at a bachelor's level, but it will expand your knowledge on a subject that most people really never learn. Next is numerical analysis. This is great for engineers and physics majors and is very applied. Many majors require it, but as you can see, you have the option to take more. I've described this in other videos, but I'll say it again. If you were asked to solve this, you could just plug in the numbers to the quadratic formula and have the exact answer come out every time. This is called an analytical solution, since it's exact and involves a formula. If you were asked to solve this though, and you were not given a calculator or anything, the best you could probably do is guess and check. But we still need ways to solve these problems fast and efficiently, especially when they represent real-world situations. So we use numerical methods or numerical analysis to solve them. There are algorithms and methods to approximate solutions like this to very high accuracy, and with enough computing power, like an actual computer, you can get basically an exact answer. For example, Euler's method can approximate the curve that is the solution to a differential equation, which many people learn in Calc 1 or 2. Newton's method can find the zero or x-intercept of a curve after running its algorithm a few times to narrow in on the answer, and this can be used to solve the problem from before. Then for those who have taken calculus, you know the integral tells you the area under the curve, but when it is literally impossible to integrate something, we can estimate the area under the curve using rectangles, trapezoids, parabolas, and so on. These are other numerical methods. They're not exact, but a good approximation, and given enough time, you could get extremely accurate. We spend so much of school learning all this math that we can do by hand, but when it comes to real-world systems, more often than not, you cannot just come up with an equation and solve it on a whiteboard to determine like the stress on an object given some force. We need computers to do the work, and those computers need to be programmed with mathematical algorithms to come up with solutions. Next, you'll notice 3 classes on abstract algebra and 3 on intro to analysis, often known as real analysis, a class on real numbers or numbers without an imaginary component that we all know of. These are really big classes for math majors, but are more on the pure mathematics side. Especially as an engineer, these are good if you want to challenge yourself and experience some courses in pure mathematics, but don't really expect to use the information you learn. Pure math courses are more about solving problems within math, rather than learning math to solve problems in physics, chemistry, engineering, etc., like you do with calculus or linear algebra. So again, don't expect many applications. I mean, abstract algebra, for example, does have applications that physicists can encounter, especially in grad school, but that does not happen until you reach a certain level, which won't really apply to a majority of people watching, most likely. And lastly, another huge field of math is topology. This is kind of like the study of shapes, but you analyze much more abstract shapes that are preserved under certain deformations. So in topology, if you can morph one object into another without tearing it, filling in holes, or anything like that, those objects are considered topologically the same. In this class, you learn about connectedness and continuity. Properties like how many holes an object has matters, whereas angles or lengths don't. That's more for geometry. And in this class, you'll even get into higher dimensional objects. One of the most famous shapes you learn about is the Mobius strip, and there's actually a fun demonstration for it that I want to show you guys. Now, topology is a pure math class, but it does have applications in computer science and computer modeling, as well as high levels of physics such as quantum field theory and cosmology, as analyzing shapes and properties within those fields is very math intensive. But I just want to acknowledge that in a previous video I talked about topology, and I saw a few comments saying, I'm doing engineering but really want to take this class as well. I just want to let you know that there are prereqs for this class, and at least at my school those included abstract algebra and real analysis, which are the pure math classes I said before that really don't have many obvious applications. So if you want to get to topology, just be prepared for multiple pure math classes first to get there, which might mean sacrificing some of the other math classes if you do get a math minor. And also know the class will be very math intensive. You will not be doing physics in higher dimensions or anything like that. It'll be a lot of proofs, and the applications would come up if you studied higher level physics, for example. Now honestly, if anything really interests you and you want to take the class, all I'm going to tell you is go for it.